All right, so we're recording now, and any questions from 12.1 problems from the textbook?
If you could we go over number 31?
Number 31. Sure. All right, and usually just to, because this is the first time we've done this together, I usually don't let people off the hook super easily. I don't mean to disincentivize asking questions, quite the contrary. Um, but I do want you to kind of give me a bit of what you were thinking, why it didn't work out, and that helps you, helps me understand where you're coming from. It also helps highlight what's going on for your classmates too, because they might have had the same struggles. So what did you try here? What were you thinking, and it just wasn't working out?
I really had a hard time getting it going. I didn't know whether to look at it as two separate, kind of like a part A, part B,
Yeah.
opposed to one whole thing. And it was pretty much the only one that I had a hard time really even getting started.
Okay, gotcha. Yeah, so when they're joined with a comma like this, and this is kind of probably the first time we've seen them in this form, right? Because we've got another variable to play with. So we got to think of them as being one system. So the fact that it's x squared plus y squared equals 4, this is the set of all points that satisfy this condition, right? And so in R2, what did that look like? X squared plus y squared equals 4. We'd consider this to be what?
Be a circle.
Yeah, just a circle of radius 2, right? So in R3, though, which is where we're really playing, what would just this equation look like?
I believe it would be a parabola.
Not a parabola, because if we add the z dimension, right, we see that z is missing from this. And so we say z varies freely, right? So z can be any value, but x squared plus y squared have to equal 4. So it's kind of like if I look down on the z-axis, or from atop the z-axis, right? Here's now my xy, here's my z. It's saying x squared plus y squared still needs to equal 4, so I still got this circle of radius 2 in the xy plane. But if z can vary freely, then what really is this thing?
It would be a cylinder.
Yeah, it'd be a cylinder, exactly. So it's something like this. Okay, so that's part 1. So that's really what this thing is in R3, but we have this extra condition now, right? Not just that x squared plus y squared have to equal 4, but also the points have to have a z coordinate of -1, right? So what do you think that's going to be? What is z equals -1 in R3? This thing on its own is what?
It's a plane perpendicular or parallel to the XY plane.
Yeah, it's parallel to xy, and it's down one notch here, right? So it's kind of a plane that lives, it's like one floor below the xy plane, right? So all the points that live on this plane have a z coordinate of -1. And we're saying that the points that we are considering right now are the points that live on this plane and on this cylinder. So if I kind of add this plane here at -1, I add this kind of basement floor to this thing. Where these are both true is going to be where? Let me draw a better plane here. So it's kind of like I got this tube where the x and y coordinates are all set, and then I'm saying the z coordinates have to be this particular level. And so it's like I'm sending a sheet of paper through a cardboard tube. Does that make sense? And so since I'm slicing that with the cardboard tube, where they intersect, where are all the points where this is true, is just on this like ring of intersection. Let me draw in a different color. Just on this ring of intersection here. And what's true on this circle? The z values are all -1, and the x plus y squareds are all, or the x's and y's satisfy this circle equation, right? So this is really the set of all x, y, z such that x squared plus y squared equals 4 and z equals -1. If you look at from it from like a set builder notation perspective. All right. So that's a good one because that throws together a few new things. The new dimension, the new notation we're using, right? This idea of surfaces versus 2D curves. It's a great question.
So when it says, like, like, because the question for that one says describe in words.
Mm-hmm.
Could you just give like the three-dimensional coordinate point that's like the center of the circle, and then say that it's a circle, centered at like 0, 0, comma, -1, parallel to the XY plane or whatever?
That last bit is the operative piece, yeah.
Is that sufficient?
Yep. Circle centered at 0, 0, -1, and parallel to the XY plane. Okay. And again, we're saying circle, not disk, right? It doesn't include all the points in between. It's the points on the boundary. Points on the boundary. Cool. Other questions on that one or any others? Okay. Hopefully you had some fun. It's kind of a new space to play in. All right. So picking up. So today, gonna extend our kind of pre-calc and multivariate idea into playing with vectors. So I know how many of us have. Better question. How many of us have not played with vectors before or forget most of what they're about? Okay. Good couple of us. Okay. So I'm going to kind of treat it like we haven't seen them before. And honestly, we tend to treat things quite differently in the math and physics worlds in a lot of ways. So, it'd just be a good refresher. So we're going to look at what is a vector. And we're going to kind of think of it in a few ways. One is as a new type of number or a new type of quantity. And we're going to talk about the different ways to represent it, how we can extend our knowledge of R3 and Rn, meaning n-dimensional real spaces, using vectors. And then we're going to look at the unique operations that fall out from this. Okay. So since it's a new type of quantity, we're kind of building this arithmetic ourselves. And so we got to figure out, all right, if this is a new type of number which has magnitude and direction, how do I add these things? How do I multiply these things? Is that even legit to do? What are we calling 0? What's our analog for -1 in this space, right? So we're going to come up with all these things. And then we're going to look at the special case of multiplication. The answer to that question is it gets a little weird with multiplication. So we come up with two analogs that turn out to have great application in the real world and in the abstract spaces. So with that being said, as a kind of an outline, let's take a look at vectors. Oh, and I have my notes somewhere. Okay. Question, what is a vector? Well, a vector is a quantity that has the following properties. It has a magnitude or length. It has a direction. That's typically kind of the modern definition of a vector. It's got magnitude and direction. There's also kind of a third implied one that I like to include sometimes, which is a sense. A vector can have a direction, right? So I can be pulling an object in this direction, and that kind of creates this slope or direction, but which way is the force going? The sense we would call where the arrow is pointing in this direction, whereas the opposite sense would be maybe in the same direction, but following backwards on that line. You don't hear this very much anymore. It's kind of old school, but sometimes it comes up as being helpful in orienting ourselves, because once we get into oriented surfaces and all sorts of stuff, we're going to be a little bit turned on our heads. So that's kind of just a little foreshadowing for later. But really, you can just think of it as having magnitude and direction. Okay? So this makes it different, and now you have to classify in your heads. Now I know two different kind of types of quantities. One that I've been working with my whole life, and this new idea of vectors. Okay? And again, we're kind of pretending that you haven't heard of vectors before. So typical numbers, which you've worked with before, just values, we call scalars. And this turns out to be a not so trivial thing that we need to kind of shake for ourselves, the notion that something's a scalar versus something being a vector. Okay? I think the word scalar is a really great name, because what have these things done in functions and applications we've used before? They scale up things, right? What is 2x? That 2 is a scalar. It scales up the input by 2, right? So you can think of this really as the scales by either multiplying, adding, whatever. But so that's what a scalar value is, just a typical number. A vector has both magnitude and direction, whereas a scalar just has magnitude only. So let's do a little kind of drill here. Go down the line. We'll see, do you think this is a vector or a scalar? So speed, what do we think? Vector or scalar?
Scalar.
Scalar. Why do you think so?
Because I can be going 10 miles an hour forwards or backwards, and you don't know.
Right. The direction is not implied in the speed. The speed is just the magnitude, right? The force. A force. Whether it be in newtons or pounds. Vector or scalar? What do we think?
Vector?
Vector. Yeah, why do you think vector?
Well, because the force has to have a direction. It doesn't just exist, I guess.
Right. Doesn't just exist. That's right. So it has a direction as well as a quantity, right? As well as a magnitude, rather. Det. What do we think? It's a sign language for S for scalar, V for vector. What do you think? S or V? Seeing one S, two S's, one vector. Yeah, det is a scalar because it's just a quantity, right? Even though it might have a negative sign associated with it, right? Meaning what you're owed a credit, maybe. It is really just a magnitude, so it is just a scalar. All right, I want you to think through these next ones here. Velocity, acceleration, momentum, energy, temperature, work, current. So which have both a magnitude and a direction and not just a magnitude? All right, so I'm going to mark down what I think and then we can debate, okay? So velocity is a vector. It has a direction associated with it, unlike speed, right? Your velocity is in the positive or negative direction, or right with some variation of that, some component of direction. Acceleration can be both, right? We can be talking about acceleration in the same way we talk about speed, as just a magnitude, but it also does have a direction, right? So that one's kind of a little tricky one there. Momentum has a direction, right? A momentum in which direction would be the next question. Energy and temperature, these things are just numerical values, right? They don't necessarily have a direction. Even though they do have a sign, we can represent all the information we need with just a positive or negative number, right? Work done is based on displacement, and displacement is a vector, right? Moving from one point to another. And then current, right, is measured in scalar. Again, all we need is a number to represent that. We don't need that other kind of dimension of knowing the direction of it. So do we have questions, comments there? Debate? Protests?
I have one question.
Yeah.
Okay, so for current, I
Mhm.
get that in theory, to represent the strength of it, you only need a number. But current does also have a direction in, like, you know what direction it's going to go, but it does still have a direction, I guess, assigned to it.
Mhm.
So I'm just kind of curious as to is it because, like, it really only has one way it can go, therefore in theory you know the direction, or like what's kind of the logic behind that?
I think that's just the logic, yeah, that it would be implied. I'm sure you could, the higher level you go, you could probably start to make some arguments against. But it just as it stands and as it's used in equations, it's used just as a scalar quantity. Yeah. If you find equations that treat current as a vector, let me know and we'll take it off the list. And we'll strike the video and we'll throw a protest. But yeah, no, it's a good point.
In general, if you're working with something that's, I mean, I realize like acceleration and velocity, like, right, there's like a weird situation there with acceleration. But if you have something that's essentially gotten from something else, and that thing that it comes from is already a vector, can you assume that your new thing's going to be a vector? Like your like your change in acceleration would be your jerk or whatever, right? Can you assume that that's a vector because acceleration normally has a direction?
Yeah, so yeah, we're getting into the weeds a little bit, but not too much. And so, right, differentiation is an operation that happens on vectors. And so you input a vector and you're going to output a vector for sure. And eventually that could be just zero, which is the zero vector, right, and not the zero scalar. But yeah, absolutely. Yep. So for that operation of differentiation, it acts on vectors. Cool. Other questions? Right on. Okay. So, a couple things that I don't love how the book, or really anywhere, does this, which is because we want to be able to represent vectors in a few different ways, and so I want to outline them now at the top instead of starting with treating them like arrows, which is what most people do, and then moving into using components, and then moving into using standard basis vectors. I want to introduce all three of those ideas at the same time, and we'll work through them in that order, but I want you to know that all these three things are the same, okay? And so just in the same way that we have, y equals x squared can be represented by a curve, a vector can be represented in algebraic notation, okay, as well. So we'll just say that. So vectors can be represented in different ways. One is really even a matrix that we don't get into too much here, but if you get into linear algebra and any sort of higher math, you're gonna play with matrices. But the first is we call like arrow form. And that's where we have some vector A, and we use this little arrow notation above, or it'll be a bold letter represents a vector. And in this picture, we recognize that this length here is what we call the magnitude of A. We use the absolute value symbol just like we do on the real line to determine, to signify the length. And then we also have a direction, okay? And so this vector A, if this is in the 2 space, it has a x component and it has a y component. How far over, how far up? This is arrow form. Oops. Okay, and if it was in R3, we'd still have that length is the magnitude, but you might have a x direction, y direction, z direction. Okay, that make up these 3 components: how far over, how far out, how far up. Again, this represents this length. So this is a really nice way to think about something geometrically, to think about vectors geometrically. It gives us an intuitive sense about how these operations should go. How do we add these things? How do we multiply these things? How do we build formulas around vectors, these forces, these things that we care about, if they're represented best by arrows. So we'll look at that in a moment, but I wanted to show you the other two forms first. Okay, so this is one way we can conceptualize them. Once we leave R3, now you're talking about four-dimensional arrows, right? So it breaks down. So that's why I want to give you the algebra right up at the top, so that you know we're talking about the same thing. So there's a component form. Where we say the vector A is given to you in its x component, y component, and z component. This tells you how far over, how far out, how far up. This assumes that you're starting at the origin. Right? There's a base on the arrow and a tip of the arrow. This assumes that the tail is at the origin. Tip is at x, y, z. Just like we have here. This is really nice. You'll also see this as a vector, sometimes as a column or a row, typically as a column vector, a 1 by 3, right? So we'll talk more about component vectors and why they're nice in a little bit. And the other thing that I'll tease now too is a combination of the basis vectors. Okay, that like here the vector, oops. If I have the vector 1, 2, this really, or let's do it like this. Let's do it in R3. Vector 1, 2, 3. This means my x component is 1, my y component is 2, my z component is 3. So if I think about this in R3, this thing comes over 1, out 2, up 3. So it's really this vector that starts at the origin and points to this point here. And what you can really think of for this vector here, so this is a component form. I'm now showing you the arrow form down here with its components listed, 1, 2, 3. Another way to think about it is a combination of basis vectors, which is really kind of like thinking about an ingredient form. So it's like taking something that's in its finished state, something that you cooked, and thinking about it instead as the different combinations of ingredients. And what are those ingredients? Well, there are 3 special vectors that we give a name to. That go along the x, y, and z axis, and they have a length of 1. And we call them I, j, and k. Now, depending on your math history and your engineering notation and stuff, the names of these things are going to change. But just know, for the most part, this is what we're going to call them. And so these are the standard basis vectors. And you can think of A instead of it being 1, 2, 3 like this as a in component form or as an arrow like this, you can think of it as one bit of I. We scale I by 1. We scale the j vector by 2, and we scale the k vector by 3. And so we write it like this. This is what I mean by as a combination of the standard basis vectors. Now again, what I'm doing here, if this feels like kind of a, like we're blowing past some stuff, we kind of are. I wanted to just highlight the 3 different names or ways we represent these things before diving into each of them, okay? So I want to first go back and play with arrow form. So we need a new set of rules and assumptions for a new type of number or a new type of quantity. We're going to kind of build our own algebra around these things. So, you know, if A is the vector that looks like this, and these sketches don't have to be perfect, and B has a little bit more of a horizontal slant to it, let's actually make it a little bit longer so this point is more clearly stated. How are we going to define A plus B? Does anybody remember how we do this?
If you want to do it by drawing it, you literally just draw them out one on top of the other, and then, if I remember correctly, the final vector ends up being the one that's drawn from the tail of the first one to the tip of the second one.
Yeah, absolutely. We call that the resultant vector. Right? So you put the tip of the second one on the other way around. You put the tail of the second one on the tip of the first one and see where you end up, right? And then you can inscribe that resulting vector, resultant, and that will be the sum. Okay. And we see that if you want to talk about, you know, rules following from the definitions, right? Our assumptions kind of generate these inescapable conclusions, right? So the fact that this is the case tells us that, well, if I took B first instead, let me move this out of the way. If I took B first instead, something like this, and added A to it, right, tail to tip, I'm going to get the same resultant vector from start to finish. All right. So what does that tell us? We just proved with a graph that we have the commutative property with addition. Okay, so with adding vectors, it doesn't matter what order you add them in. Okay, so that's a good thing. We want addition to be simple. To get kind of a visceral sense of this, and you know what a resultant should be, think about standing on opposite sides of a box, so like here and here. You and a buddy are pushing on this box from opposite sides. Think about what the resulting force should be, or what the resulting action should be. And then think about maybe if you instead were both standing on kitty corner sides of the box, right? What should happen? The resultant should be out in this direction, right? So you've got this guy's force plus this guy's force. And so it should end up going like in this direction. And again, you can think of it as being drawn in tip to tail, like that. Okay, so you kind of generate this parallelogram when you add. And the diagonal is that resultant vector. Okay, not too bad. How about, so that's addition, it's commutative, this is how we add it. How about scaling or multiplying? So if I have C times some vector A, where C is a real number, again, I think I told you guys last time, I'm going to use this notation a lot. It means this is a member of this set. All right, so C is just a real number. What should this be? Well, C is this scalar multiplication. And so what it does is it takes the vector A and it keeps its direction the same, but stretches the magnitude. Stretches or shrinks, depending on if it's less than 1, right? The magnitude keeps direction. It also, instead of flips, let's use a better word there. It also reverses the sense if C is less than 0. All right, so if I have A is like this, then CA, if C is like -2, let's say, then I should have a vector the length of 2 times A, but now it's pointing in the reverse direction. Okay. Shouldn't use too many arrows when we're talking about arrows, so I'll delete that one. All right, so it flipped the sense. So it's still, right, parallel to its original direction, but it's running in the opposite way. Question?
Yeah, the tip of CA is also the tail of A. Like they're the same point.
The tip. Okay, good question. It would be that the tails are the same. Maybe just because I drew it that way, it was it would be more like this.
Cool.
Yeah, good clarifying question there. Good. No, so the tail remains the same. It flips the whole thing around 180 degrees. Okay. Good. So we know how to scale these things. We know how to add these things. Some other stuff we should know. There is something called the zero vector. Where it has this property. And if we think about this, geometrically, it's pretty trivial. If we think about it algebraically, it's really where the rubber meets the road, right? We need something with 0 as its components in case we, nullify a force, cancel something out. We need that structure to exist. So the zero vector is going to be different than the number 0. And there's going to be times where we need to care about that, right? When is it a vector? When is it a scalar? Okay. So we've got that. We've got the zero vector. We can scale these things. Some other nice corollaries here, which is, A plus -1 times A. Or you can think of it as, A minus A. That's going to get you the zero vector, right? Because what's this going to do? Start you down on A, put the tail to tip, and then reverse the sense, and I'm right back where I came from, right? Okay. We need to remember that the magnitude is the length of A, which now we're going to need a little bit more than just an arrow, right? Because we're not going to carry our ruler with us, so we're going to need to venture into the algebraic realm. And what else did we need? I had something else here. Oh yeah, how do we multiply? Vectors. Short answer is we can't. The long answer is we kind of can, and we're going to unpack it over the next 2 sections. All right. So there's something called the dot product and the cross product. And we'll get through this one today and this one next time. Because the fact that these things have a little bit more going on means multiplication isn't going to be as simple. They're going to have different meanings and different physical motivations. All right. So some terms to know. Oh, and I remember what the other one I was going to say. If you have a little bit of space to drop in one more bullet point up here. I know not everybody can copy paste if you have actual paper in front of you. Last one, we say that A is equal to B. How do we claim equality of a vector? We kind of have it. It's pretty intuitive, right? If all a vector has going on is a magnitude and a direction, then if 2 vectors have the same magnitude, same direction, we're going to say they're the same thing. Okay. Now I could see someone taking beef with that, right? Which is a force of, 3 newtons due northwest at a placed at the top of my head versus placed at the center of my body. Those are not, really equal vectors, right? The forces aren't resulting in the same action. But in terms of having the arithmetic work out, we do say 2 things are equal if and only if the magnitude of A equals the magnitude of B, and they have the same direction and sense. Okay, so that means if this vector is, way up here in the xy plane, and this B is down here, oops, that is not the same. Since they have the same direction and sense, if we kind of just teleported them back or translated them back to be tail at the origin and tip out in space, then we say they're the same thing, right? If they're sitting right on top of each other. And so what I did just there is actually point out my next point, which is that the free vectors are vectors that just kind of live in the geometric space. They're out there. Whereas a position vector is talking about all the ones playing from home base, playing with the tail at the origin. So an example of this would be, the vector from point A, which is 1, 2, 3, to point B, which is 4, 7, 9. This is, again, some vector. It's in octant 1. It's doing something like this. Nothing too crazy. Again, just a rough sketch here. And, this is out 1, 2, 3, 4, 7, 9. So here's A, here's B. And that is what it is, but we usually work with position vectors. And the reason is because they're a lot nicer to work with. So as a position vector representation of this, what we would do is say, well, the vector AB is really given by, and I'll use the component notation here. Actually, I won't do that yet. I'll say starts at 0, 0, 0, ends at, I find the difference of the x positions. All right, so how far over, how far out, how far up. So that 4 minus 1, 7 minus 2, and 9 minus 3. And so what point is that really? It's 3, 5, 6. We'd say this is the equivalent vector. And so since this is a position vector, it starts at 0, 0, 0, it ends at this point, we call this the position vector representation of AB, and we use this notation 3, 5, 6. Since they all position vectors start at 0, 0, 0, we only care about their endpoint. Okay, so these things are the same. So these are nicer to work with. And they'll be the basis of a lot of our calculations, okay? So, and again, since any two vectors that have the same length and direction, and those are preserved when we do this, we'll just work on position vectors. All right. So now a quick side note. That's not really a side note. It's something that I want to be cooking in your brain for the rest of this course, which is that any point now has a double meaning to you. So the point P1, 2, 3 is the point in space that's meaning 1. Meaning 2 is there's the position vector starting at the origin, and its tail is at 1, 2, 3. So anytime we're thinking of a point in 3 space or 2 space, so let's say here's P1, 2, 3. You can think of it as a point, but you can also think of it as there's a vector being drawn from the origin to this point. Same here. Here's P1, 2. I can think of it as a point, or I can also think of it as a vector from the origin out to this point. Okay, so I want you to kind of start getting used to that idea of point in space and also the vector pointing to that point in space. They have that double meaning. All right. So now that we have that settled, and we want to be able to compare vectors and say, are you equal, are you not, right? And build this whole arithmetic around them, we need to be able to figure out how long they are. And what we just did, writing this in component form, allows us to do that. So computing magnitude of vectors. How do we find the length of a line segment in R2 or R3? Well, we played with this a lot last time, right? We used the distance formula between 2 points. So for A equals, let's call it the magnitude of A. How can we find the length of this thing? Well, if it's over 1 up 3, right? How would I find the length? Okay, good talk. We just do the distance formula, Pythagorean theorem, right?
Every 1 squared plus 3 squared.
Right. Thanks. All right. I know we can get on a roll here. But yeah, the length is radical 10. Length of that hypotenuse. Right? And so if we have a B that's 1, 2, negative 2, then the magnitude of this thing, I'm going to use that to compare to other vectors or whatever, square root of 1 squared plus 2 squared plus negative 2 squared, which is square root of 9, which is 3. So the length of B is 3. Magnitude of B is 3. This is also called the norm in more general vector spaces. Okay, so for those of you becoming math majors, you hear magnitude and norm as the most general kind of use of the absolute value. Okay. All right, so I'd like to stop talking for a minute, give you guys a chance to work with this real quick. So I'd like to say find the magnitude of this guy this guy, and this guy. Oops.
Do you want us to simplify the radical for A?
If it works out that you can, yeah, but don't get too excited. So for A, what do we do? Square up all the components and then add them, right? And then take the square root. I want to note here too, sometimes thinking of the quadrants is helpful. Quadrants is the square of the distance or the square of the length, so the square of the magnitude. Instead of just dealing with square roots all the time, sometimes it's better to just kind of play with it as a square. But that's rare. So we should get square root of 134. For B, when we square these both and add them up, we'll get a magnitude of 1, and the same happens with C. And for a really silly but important example, what if I had 0, 0? The magnitude of this is really 0 squared plus 0 squared, which is 0, right? So the 0 vector has magnitude 0. We can kind of prove that, which is nice. Are B and C equal? They have the same magnitude. Your thoughts?
No, because in spite of having the same magnitude, B doesn't have a z defined, therefore it could exist anywhere on Z, as where C does have a z defined, so it can only exist there.
Okay, nice. Counterpoint, however, is that C does live in the XY plane. So what is some added evidence?
They don't have the same direction.
Yeah, they're not pointing in the same direction, right? If you think, you're gonna have to think about these a little bit more spatially to get that, which is this. Although it lives in the XY plane, it's pointing out on the x-axis a length of 1, right? Whereas this guy, B, is pointing into octant 3, right? Which is like back over there. So they have the same length, but they're different vectors for sure, right? Because they have a different direction. So good stuff. C is actually one of those special vectors. This is one of the standard basis vectors. This is actually I. Okay, it has a magnitude of 1, and it's pointing purely in the x direction. And so then the follow-up thought there would be that J is 0, 1, 0. It points purely in the y direction with a magnitude of 1. And then K is 0, 0, 1. It points only straight up in the z direction with a magnitude of 1. Why are those helpful? Well, because now we can talk about vectors in terms of their basis components. It's like, salt, pepper, water, whatever, ingredients to the vector itself, which is really, really helpful. We can scale them up now that we have units, right? Okay. So any vector with magnitude 1, so these are, I'll write it again here, these are standard basis vectors. They have the special quality in that they are mutually orthogonal. What does it mean to be orthogonal?
They're like at 90-degree angles.
Yeah. Another way to say perpendicular. So they all form a 90-degree with each other, with each of the other two. So that's a special property. It's required that be the case in order for it to be a basis vector, meaning you can generate every single vector from these vectors. Okay, so they are super important. You can't really do that with any 3 vectors in the space. So that's why we care about these 3. But we do say that any vector of magnitude or length 1 is a unit vector. And we care about that because if you have a vector where you only really care about the direction, which we're going to have frequently, then the magnitude might be meaningless. We can strip that off and just preserve the direction with a magnitude of 1. Then we can scale it however the heck we want. right? Which is really nice. So for a given vector A, and let's just give ourselves a simple example of 1, 2, you can find the unit vector in the same direction as you take A and you divide it by its own magnitude. And so how do you divide a vector by something? How do you divide its components by something? Well, we haven't gotten to that yet, but I'm going to show you right now. You essentially multiply scalar multiplication against the vector itself, and that becomes 1 over the magnitude of A, 2 over the magnitude of A. Each of the components gets multiplied by this scalar. And what is the magnitude of A in this case? Well, it's the square root of 1 squared plus 2 squared. So it's radical 5. So that's where we got, well, it's not exactly the first one, but it's darn close. Pointing in the opposite direction. But this is how we find the unit vector in the direction of A. There's no such thing as a unit vector. You can go invent it. They'll probably name it after you, but there's no such thing. All right, so how do we add and scalar multiply in component form? And I'm going to add the standard basis form to this as well in a moment. Well, if we add tip to tail on vectors, that means we're adding how far over in the x direction, how far up in the y direction. So it becomes we add their components. Okay, and if it were 3-dimensional, all this holds up. And what's good about this, oops, a little error there. I'll actually write it like this. This holds up to n dimensions. What you do is you add the components for each slot. X direction, Y direction, and the N direction. Okay. That's how we add things and how we scalar multiply. Is we take C times A1, A2 up to AN, and each of those components gets multiplied by C. Scalar multiplied. Okay, so it stays a vector, but all those components get scaled up, right? So if we multiply something by 2, so if A is, 1, 2, 3, Mally, you love that vector a lot. I sure do. Then, 3 times A is 3 times 1, 2, 3, which becomes the vector 3, 6, 9. Okay, so you can see how it will keep the direction of A, but just scale up its magnitude by scaling up its ingredients of I, J, and K, or X, Y, and Z components. So, similarly, we can write A as the component, how far in the x direction times that basis vector I, how far in the y direction times that basis vector j, how far in the z direction times that basis vector k. Remember, these are the three ingredients, x, y, and z, those directions that, or those vectors that make up the entire vector space. So the same stuff holds up. CA is going to be C times this whole thing. Which is CA1I plus CA2J plus CA3K. And A plus B is really going to be, A1 plus B1I plus A2 plus B2J plus A3 plus B3K. I forget who said this, but it was a math teacher, and he was talking about how people only remember certain things when they leave the math world, right? People who get off in calculus, they remember that, I think you add the exponents, right, when you multiply two bases together. And I remember that you got to get like denominators for fractions. And what people remember from Calc 3 and engineering is that you break vectors into their components, right? So it's like one of those kind of base level things that you got to drive into your brain, that what do we do with vectors? We break them into their components. So that's how we add those vectors. You know how to get unit vectors. That is pretty much all of the base definitional stuff. Okay, here's a question. Show me if these two vectors are parallel or not. If A is 2, -4, 1, and B is -6, 12, -3. And while we're here, we'll write them in their component form too. What do you think? Just by looking at these things in component form, are they parallel?
I'm gonna guess yes without doing any calculation.
Nice. Throw it to the wall, see if it sticks. Why do you think so?
If you divide everything in B by -3, it becomes A.
Yeah, right. So we could say that just by looking at the components, right, that if I factored out a -3 over here, I'd be left with 2i minus 4j plus k. All right, and what did we call this? This is just a. So this is really just -3a. So what's happening here really is that b is -3 times the vector a, so -3 scaled of a, and so it has done what? Made it 3 times longer and reversed the sense, right? Reversed the direction. So it flipped it, 180 degrees, not really because we're in 3 space, right? But flipped it the opposite direction. So reflection through the origin, right? I'm pointing backwards. So yes, they're parallel. But since this is where that kind of place where they have a different sense. So if you can show that one is a linear multiple of the other, then you know that they're parallel. Okay, so that's nice to know. So another question is, find a unit vector that points in the same direction as -5, 2, 1. So what do we think here?
You would just calculate the magnitude first, and then you would do the division that you showed earlier.
Absolutely, yeah. So we calculate the magnitude, right? It's going to be the square root of 25 plus 4 plus 1, radical 30. And then we're going to scale it down by its own magnitude, right? This thing is radical 30 long. If I divide all the components, all the ingredients by radical 30, now the total length is going to add up to 1, right? And that's what I want. I want to preserve the direction, but not the magnitude. So then that unit vector in that direction is going to be a over radical a. So that is exactly, yes, just -5 over radical 30, 2 over radical 30, 1 over radical 30. Awesome. I'm going to give 30 seconds and ask if there's any questions, concerns, comments, exclamations of joy or glee. Okay. I'd like you to head to page 842. I feel like we did quite a bit of work to unpack the basics of building these things. But page 842 gives you the properties of vectors. And I feel like you're at a place where you could prove all of these, play with some of the proofs there, and sort it out yourself. And we're going to start on the dot product now, which is one of the ways that we can multiply vectors, quote unquote. But we won't probably finish it. So we'll pick up with this next time as we then jump into the cross product. Okay. All right. So now we've got a lot of it really, of what vectors are. I'm going to look at the dot product, right? I'm going to try to answer the question, what does it mean? And how does it look to multiply two vectors? Or even three vectors. Well, the motivation here actually comes from the physical world. If we remember, work is force times displacement. And I don't know if we talked about work actually at the top of classes, whether it's a scalar or a vector. But work done is actually a scalar quantity. Okay. And so if you remember, work done is force times displacement. Force and displacement are both vectors. And we learned the easy version of this in grade school, which is just the amount of force times the distance it moved, right? But it's really only the work done in the direction that it moved. Okay, so it's a little bit more complicated than that. So this needs a little bit more work, but how it pans out, and if you look at a little bit more sophisticated definition of this, is if you take the magnitude of the force and the magnitude of the displacement and then multiply it times the cosine of the angle, where theta is the angle between the force being applied and the displacement, right? And this aligns with what you expect, just right. If you have a leash on a dog, right? If the force is straight up, right? The work done, there's a 90-degree angle, the cosine of that is 0. You're not moving the dog in any particular way. If you're, I mean, nobody walks their dog like this, but if you pull the dog behind you and it's horizontal, you're doing the most amount of work, right? Because it's perfectly aligned with the horizontal direction. But if it's any angle in between, then you're talking about a fractional amount of the force being actually applied to do the work, right? So that's where that cosine comes in. This kind of does the scaling of the magnitudes. And this is why I sometimes call it, especially in R2 and R3, we call it directional multiplication, is the dot product, because this cosine, what do we remember about cosine? And this is why I put on the sheet to review your basic trig stuff, which is that at 0 for t, or for theta, at 0 it's at its max of 1. At 90 degrees it's at 0. So when the two vectors are perfectly aligned or right on top of each other, the theta is 0 and I'm at maximum amount of work. And when it's at 90 degrees, the cosine is 0, and that drops this whole thing to 0, so there's 0 work done. So that's a motivation for this dot product, and we call it, in air quotes, directional multiplication. I'm one of 3 people, by the way, that I've heard say that, so don't take that on the road and expect people will know what you're talking about, but I find it makes intuitive sense. So what the dot product is defined to be, I want to give this to you so that you have it to play with. A dot B, does that keep happening? A dot B is defined to be this way, like we said before, the magnitude of the vectors times cosine of theta, where theta is the angle between the two. But this is actually a theorem that's as good as the definition itself. The actual definition says you take the components and multiply them together. Not C. A3, B3. And again, this works up to n dimensions. We're probably only going to care up to 3 or 2 for a while. But what do we get is a sum of the product of all the components, which, if you think about it, makes sense, because if they're closely aligned, the components are going to scale each other up, right, and make a larger product. If they're pointing in different directions, it's going to end up shrinking that down in the same way that this cosine does that same thing. Okay. So, as an example, find the dot product of A, which is, let's come up with one I've done already. It doesn't matter. 3, 4, 5. And B, which is 6i minus 2j plus 1k. Kind of blending some stuff together here. Well, A dot B we said is the components A1 B1 plus A2 B2 plus A3 B3. And so the components here are 3 and 6. So that's 18. 4 and negative 2 are my y components, right? So that's a minus 8. And a 5 and a 1, these are my z components. That's a plus 5. So I end up with 18 minus 8 plus 5, which is 15. Which is what type of number?
Scalar.
That's a scalar. So we multiplied two vectors together, and we ended up with a scalar. Okay? So this is why it's also called the scalar product. And the inner product is another name for it. It's the more general name for this operation. It's very, very important to note that the dot product ends or results a scalar. Okay? And we use the dot to represent it. The other important thing to know is that, right, we have this as the definition of this directional multiplication, multiplying these two vectors components together, ending up with a scalar value without knowing the angle between them. Okay, and that's because we had their coordinates. We can actually go ahead and find the angle between two vectors by just setting up an equation, that 15 would be equal to magnitude of A, magnitude of B times cosine of theta. I'm going to leave that to you guys to do. So say find theta between A and B for this above. And you're showing really that 15 is equal to magnitude of A, which you can find, magnitude of B, which you can find, cos theta. Go ahead and solve for that angle between the two vectors. But important points. Dot product gives you a scalar, and it's a way to both access the angle between two vectors and get around it if you don't want to deal with it. Okay, so there's a lot of geometry and geometric problems that get wildly simplified by this theorem here. Okay, and I don't know if you got to review this in your travels. But remember, for a given triangle, if this is your hypotenuse r, and here's your sides x and y, that really x is r cos theta, and y is r sine theta. Super important to know, right? So if r is 1, this length is really just the cosine, and this length is really just the sine of the angle. The top use that we use that theorem for, maybe not the top, but it's in the top 3 for sure, okay? And the top 3 use of this is to find if two vectors are orthogonal or not. How would this help me do that?
equal 0 if they are, right?
Exactly. So that's another big idea that we'll use a lot. Okay. Let's do an example with that, and then we're going to call it there. I'll get to projections next time. I think we actually got about as far as I expected to, which is shocking. So if you see practice problems come up about projections, feel free. It's not beyond you at all to just glimpse at the few examples in the text, but we will pick up with those next time. But let's do an example here. So if u is 2I minus j, and v is negative 1/2 I plus 1/4 j. Well, we test it by taking the dot product, which is 2 times negative 1/2 plus negative 1 times 1/4. So we'll get what? Negative 1 minus 1/4, which is negative 5/4. So are they orthogonal? No, they're not. But what we can also extend this idea to notice is that the magnitude of u is what? Square root of 2 squared plus 1 squared, which is radical 5. Magnitude of v is square root of 1/2 squared, which is a fourth, plus a fourth squared, which is a 16th, which is going to be what now? 5/16, so radical 5 over 4. And so we saw that u dot v was equal to negative 5/4, which is really equal to, if you think about it, negative radical 5 times radical 5/4. Which is the opposite of the magnitude of u times the magnitude of v. And so what does that imply?
Well, you've removed the direction, which would explain why it's scalar.
Yep. It's definitely a scalar number. We know from that theorem that this is supposed to be the product of their magnitudes times the cosine of the angle between them, right? what does this imply here? Well, if I set these equal, it's been a long day, y'all. If I set these equal, magnitude of u, magnitude of v, cos theta equals -1 times magnitude of u, magnitude of v. These are just scalar quantities, so I can just cancel u, cancel v. Cosine theta equals -1. What does that tell us?
It's a difference of 180 degrees.
Yeah, difference of 180 degrees. Right? At pi or 180, cosine's at -1. So they are parallel. Just with the opposite sense, right? But if the dot product were 0, that's a quick way to check and see, are these two vectors orthogonal or not? And so that's one of those skills that I'd like you to, since it's so easy to calculate, even with three-dimensional vectors, right, to just multiply their components and add them up, that you should essentially be doing that almost before starting a problem, right? If it's not called for, don't do that. But it's one of those things where it's low cost, tells you a lot about the problem. And if you know that that dot product's 0 right out the gate, you know you have orthogonal vectors, and that tells you a great deal. Okay. So if you're curious, eager, and your coffee hasn't worn off on you yet, you can jump into page 849. Nope, I lied. 850 and 851. And you can read a little bit about projections and the direction cosines, but that's where we're going to pick up next time. And again, we decided we'll be doing these live, so the recording will go out tonight. And your first problem set should be posted by tomorrow. I think I'm going to make that due the following Tuesday. Okay. And if it, for whatever reason, we don't get where we need to on Thursday, we'll be flexible and shift. But any questions before we call it here? All right, we having fun yet? Yep. Go ahead.
Just a point of clarification. When you say that the first problem set is due by tomorrow, that means tonight at 11:59, right?
Oh, sorry. I said I'll post the first problem set tomorrow.
Okay. Never mind. I'm sorry.
Yep, no worries. And then it would be due Monday night at 11:59. Yeah. But if that changes, I'll put out an announcement in the Blackboard course. Other questions, comments, concerns? Awesome. So again, you've got some problems to do in 12.2 and 12.3. Stuff about projections. Just know that we haven't covered that yet, so give yourself some flexibility. Otherwise, we'll see you then.
All right.
All right, y'all. Take care.
Is this different than the online practice problems?